In this video, we'll talk about column spaces. We'll define what it is, and then we'll look at some examples. The column space of an m by n matrix, denoted col A, is the set of all linear combinations of the columns of A. So if A is the matrix with columns A1, A2 through AN, then the column space of A is the span of A1, A2 through AN. In our linear transformation video, we mentioned that the image of a matrix transformation is the column space of that matrix. So let's see why. Remember that the image of a transformation is the set of outputs. If I input an arbitrary vector x equals x1 through xn, then the output t of x is a times x. So if A has columns A1 through AN, and X has entries X1 through Xn, then this matrix multiplication will give us X1 times the vector A1 plus X2 times the vector A2, and so forth, plus Xn times the vector AN. So as you can see, the output is a linear combination of the columns of A. So taking all possible inputs in our domain, meaning all possible x1 through xn, this is going to give me all possible linear combinations as outputs. That's why the image is the collection of all linear combinations of the columns of A. Another remark is that the column space of A is a subspace of Rm. This time we don't really need to check the three conditions to verify that it's a subspace, because I know that the column space is a span of vectors. And we learned that the span of vectors always forms a subspace. Now let's look at some examples. In our first example, we have A equals 1, 2, 3, 4, and we're asked to find the column space for it. All we have to do is write down the column space as the span of the columns of A. So that's 1, 3, and 2, 4. It's just that easy. Let's try another one. So here we have the matrix B with entries 1, 2, -1, 4, 2, 4, 3, 3, -1, -2, 6, -9. The column space of B is going to be the span of the columns of B. So that's 1, 2, -1, 2, 4, -2, -1, 3, 6, and lastly 4, 3, -9. And that's all you have to do for now. Before we end this video, I want to talk a little bit about the span of vectors. When we look at the span of one vector, we typically have a one-dimensional space, right? If I draw my xy plane and I draw a vector, then the span of that vector consists of all scalar multiples of that vector, which means that I'm going to get all vectors along this line. Next, the span of two vectors is typically a two-dimensional space, a plane. If I draw my xy plane here and I put two vectors on the plane, then any point on this plane can be written as a linear combination of those two vectors. I can go a certain amount in the direction of the first vector, then go a certain amount in the direction of the second vector to reach my point. So if I take the span of those two vectors, meaning take all possible linear combinations, then I'm going to get every single point on the xy plane. In 3 dimensions, I get something like this. I have my x, y, and z axis, put two vectors here. Then the span of those two vectors is going to form a plane that goes out like this. In general, the span of n vectors is typically an n-dimensional space. However, this is not always true. Sometimes the span of n vectors could have dimension less than n. For example, let's say I have the span of the vectors 1, 1 and -1, -1. If I were to draw this, I have a vector 1, 1 going this way and a vector -1, -1 going this way. No matter how I take linear combinations of these vectors, I'm always going to stay within this line. I'm not going to be able to get out of it, so the span is a one-dimensional space rather than a two-dimensional space. Let's take another example. Let's say A is 1, 2, 3, 6, -2, -4. We can say that the column space of A is the span of 1, 2, 3, 6, and -2, -4. As we see here, the column space is a span of 3 vectors, but is it a 3-dimensional space? The answer is no. These vectors belong in R2, so at most it can only be 2-dimensional. The important thing to remember is we need linear independence. The span of n linearly independent vectors do form an n-dimensional space. So if we want to understand the image of a transformation, or the column space of a matrix, meaning I want to know what dimension it is, I need to trim the span down to a linearly independent set. And that's what we'll talk about in the next video. Thanks for watching.